analyze something, because if we get millions of data every day, it is not possible to hire so much persons. So, therefore, fast neural methods can be useful they should be introduced to work with this big data we get in astronomy. The time of Einstein has gone, and for now there is a time of iPhones, and soon we will get self-driving cars and artificial intelligence instead of humans in a lot of professions. So we have to deal somehow with it. And in IT industry, for example, through the past 5-6 years, there are a lot of new softwares, there are a lot of new paradigms, methods that are applied related to the machine learning. So it's time to implement these methods into the science too. Let me provide you a few amazing examples about the machine learning. In 2008, there was an epidemic in the US, a pandemic of flu. And it was funny that Google was able to predict how this pandemic would spread faster than FDA, US medical organization. How did Google that? How is it possible? Google has no ideas about what is flu all about. Google has no medical data. How it is possible to do? That's easy. What Google knows. When you search something, when you type something in Google, Google saves your search query. Also, Google saves your location. So, if for example someone has a flu, what the normal person, X generation or Z generation does right now? Google for drugs, for something related to that. So Google was able to see how much search queries per given location related to the flu were. So that's how Google was able to predict. So imagine, Google is not a medical organization, no medical data, no idea what is flu about, but he was faster. He was faster than all government organizations. Another amazing example is about Twitter. In 2014, on the West Coast in San Francisco, there was an earthquake. And again, Twitter was able to predict how the earthquake would spread faster than any government organization. The solution was very simple. Twitter just analyzed the tweets. Okay, it's like strange, Twitter tweets. But anyway, Twitter analyzed the tweets. The users were writing about earthquakes, so Twitter was able to see where is this user from and how the earthquake was spreading. So this amazing example shows that even if you have no ideas what are your data all about, you still can do something. And that's how machine learning, that's how artificial intelligence works. There are some research in astronomy related to the machine learning. There are only a few of them that I have outlined on this slide. It's like about, for example, detection of outliers. That's a really good task for machine learning. Or filtering a large number of false positive straight detection of near-Earth asteroids. We have a lot of new spacecraft missions that would be launched soon. So we have to analyze this data. A lot can be done by the computers and much more using machine learning. So in astronomy and in astrophysics, there are a lot of works. Okay, not a lot of, but a few of them. So it's time to implement this method also to the celestial mechanics problem. So let me tell a few words about the types of machine learning. There are actually 3 types of machine learning. The first is called supervised learning. It is very simple. I mean, if you have for supervised learning, you should have a training set. So in general, what is machine learning all about? You have input data, something like, for example, in astronomy, you have the 7-meter axis, eccentricity, inclination, some other data, and the output. Output can be different. It can be Boolean, for example, I don't know, true or false. It can be labeled with some types. So machine learning is about transform input to the output and black box in the center. So supervised learning is where you have a training set where you know the inputs and you know the outputs. So you create a model that can be trained on this set of data, and then you expand this model to the whole set. So this is how supervised learning works. Unsupervised learning. In this case, you do not have the training set. Unsupervised learning is all about finding the hidden patterns. For example, as asteroid family classification, you have to cluster somehow the data. That's a good task for unsupervised learning. And reinforcement learning. In this case, again, you have no training set, but you have a special algorithms that would provide you reward in some cases. And based on this reward, you get you can train your model. So let me talk a little bit about the methods of machine learning. There are plenty of them. I would tell you about some simplest methods, 2 of them, and outline some others, just to show you that they are very simple. The simplest method is called k-nearest neighbors method. It is very simple. I mean, imagine that you have 2 classes of objects, class 1 and class 2 in blue, green and blue. And you have to calculate. Here, for example, this is object, you want to classify it either to class 1 or to class 2. So, k-nearest neighbors method says that you should map it to the class. You take, for example, 3 nearest neighbors. And if there are more objects from class 2, then it should be, in this case, if we take k equals to 3, then this object should be classified as class 2, because there are 2 blue and only 1 green. If you take more neighbors, for example, like 5, in this case the classification will be another. So k is the parameter that has to be chosen depending on the situation. Of course, this is a very simple approach of that. There are much more complication to this method in order to make it more precise, more accurate, but this is how it works. In this method, you should also have the metric. For example, I can refer to the talk yesterday from Professor Kolchavnikov about the metric in Kepler space. You should somehow calculate the distance. You can use Euclidean metrics, you can use Minkowski metrics, you can use Kolchavnikov metrics, you can use Zappala metrics that was introduced specifically for the case of families. So any kind of metric can be used. Another very simple method is called decision tree method. It creates a binary tree with binary output of each node. By the way, this is a real decision tree. It is created for the case of Titanic. That's a very famous problem for machine learning. You have Titanic, you have like thousands of not participants, thousands passengers. Yeah, some of them died, some of them are not. So, is it possible to create a decision tree that would predict should this person die or should not, depending on first name, last name, gender, age, and class, like first class, second class of the passenger. So, yes, it is possible with 80% of accuracy. By the way, the most important is the gender of the person, female or male, in case of Titanic. So, you create such tree and then identify based on the output. Of course, this method can be improved. For example, there is a method called gradient boosting over decision trees, where you create a linear combination. You create, for example, 10 decision trees and then create a linear combination of them. So you have several weak voters, weak algorithms, and you combine them into one more powerful. There are logistic regression, neural networks, so a lot of them. But they are not so deep. Okay, how all this stuff can be applied to the astronomy and to the celestial mechanics? So I will tell you about 2 implementations. The first one that was published this year is about identification of asteroid trapped inside 3-body resonance. The idea was very simple. There are asteroids trapped inside of the 3-body resonances in the main belt. So how we usually identify them? We integrate the orbits. Okay, we integrate the equation of motion of the orbits of the asteroids in the main belt. Then we calculate the resonant argument, check is it liberating or not, or circulating, and then identify is it resonant or it is not. So if we want to identify 3-body resonance for the main belt, for ASDIS catalog, we need, if we have like 10 computers, 10 average computers, we need about 5-6 months to do that. So that's the real numbers because I did this work in the past for my PhD. For machine learning, it would take, how much? How do you think?
An hour.
Less. 10 seconds.
Wow.
The same work can be done in 10 seconds.
Without numerical integration?
Without numerical integration. Yes, this is exactly the work. I can show you some plots. So here is an example of the resonance for Jupiter minus 2 Saturn minus 1. So the green one are the resonant asteroids, the red one are non-resonant asteroids. As you can see, here are two classes, exactly for machine learning. So, and here are the results. So, gray are the asteroids that we have identified in the past. So, they were used for supervised learning as training set. Black are the asteroids that have been identified using machine learning. So, they are really resonant. We have double checked this with numerical integration. Green are false positives. So, machine learning method identified them as resonant, but they are actually not. And blue is false negative. Machine learning has identified it as non-resonant, but it is actually resonant. So as you can see, it looks really good. I mean, maybe it is not very good looking, but let's go to the numbers. There are three important numbers, three important metrics in machine learning. The first one is called recall. Recall means how much true cases we have left. In this case, how many resonant asteroids we have missed. So 100% recall means that we have not missed any resonant asteroid. 0 means that we have missed all of them. So as you can see, 98% of resonant asteroids have been found. So that's really cool. Precision. Precision is all about how many false positives we've got. So in other words, how many asteroids we have identified as resonant, but they are actually not. So these green cases. So precision, okay, for me it's really good because we have like 10% more, so we can easily integrate them and understand. And accuracy. Accuracy means how, so on each asteroid we have made a decision, true or false, resonant or non-resonant. Accuracy shows us how many times we made wrong decision. So accuracy is really cool. So it means that you can apply this method easily to the identification of the asteroids using supervised learning and get the results in seconds instead of months of calculations. Another application that is still ongoing, so I would show you some preliminary results, is related to the asteroid families classification. So the idea was the same. We have a catalog of asteroids, we have a catalog of asteroid families. We can take like hundreds of candidates for the training set, train the model, and then try to identify do this asteroid belong to the asteroid family or not. So here is the plot. I will show you on the next slide some numbers. Again, gray, these are the asteroids that are not in this specific family. The family is the Hansa family. The black dots are the asteroids that are in this family, and the green are false positives. There are not so many of false positives. You will see this on the next slide. So let's go to the numbers. So for the Hansa family, recall 100%. So we haven't missed any asteroid. All of them have been identified with extremely simple method. Precision is not good. This is something what we are working on right now. The precision looks okay. For me, it looks really okay because 80% that I removed like 80% of computational time. But still, this is something that can be improved with the methods, with other methods, or with improving of KNN methods. The accuracy is good for all cases. So for all families, we have done this work for all families, preliminary work. Recall is about 98%, and it can be improved. Why I'm telling you? Because why it can be improved? Because we did the same work for the resonant asteroids, and we got in the beginning the same results, and then we worked a little bit to improve the model, to improve the method, and so on and so on. So the precision is really the key, but we know how to improve it. Accuracy, okay, it is okay. So Generally, it means that, and again, how much time? How do you think it took?
It's probably less than a second or something.
No, 3 seconds. 3 seconds.
Okay, but the verification took how much time?
There was no need in verification because we had a catalog
No,
provided by the
to identify falses, you had to check it. So how much time took the checking?
Here?
Provided
Yeah. For now we have the output, so we can check it very easily. In future, I mean, when we identify, for example, more 500,000 of asteroids, we don't need to check them because this method is already working. So statistically, we can say that in this family would be this number of asteroids. So, as a conclusions, generally, that's it. This is the conclusion. It works.